Hello everyone, my name is Stefan Hubey, your houseboat expert. In the background, one of the boats I built, and as well the author of the book Designing and Building Houseboats. Thousands sold, and I'm really happy that so many people turn to me uh, to tell me about their projects, and I'm getting stoked about helping them. So this is just a small presentation about little things I think are helpful. These are kind of the chapters of the book, and today we take something out of the area how. Uh, I want to talk about providing safe freeboard and buoyancy reserve. So it's all about that your boat is not too deep in the water and you have enough volume in the hull to keep you afloat in all circumstances. Okay, let's take a boat here with some catamaran hull, two round hulls. It's somewhere, it's floating. Hopefully not too deep, hopefully not too high. If it's too deep, it's unsafe, it's too high, you spend too much money on the hull. So, but how do we find out where it is? We have a waterline. The freeboard is the distance from the waterline to the top of the hull where water potentially can run into the hull and cause it to sink. On the other side, you have the draft from the waterline to the deepest part of the hull. Um, Very interesting as well that yes, we don't want to have water running into the hull and into our living room, but as well we want to keep like parts that can rot dry. So the clearance to any through hulls where water can run in or timber like cross beams is as well important to consider. How do we calculate the draft and the freeboard? So we have the weight of the boat. F stands for force, so the force, the weight force, pushes the boat into the water. On the other side, you have the buoyancy force pushing it out. So it's in this kind actually two forces left and right, but for simplicity reasons, we make it one. It's again a force F and we call it buoyancy. F, buoyancy force. Um, a stable condition, that means the boat is not going deeper in the water, not going higher out, is when F weight is F buoyancy. Simple, that's it, very simple. Um, and like these forces are calculated in Newton. That's the correct term when you talk about forces. But in general, we make it a bit simplified and we just use the equivalent in kilograms. And 1 Newton is about 0.01 kilograms. Okay, weight is as well called displacement with the boat builders. And it makes a lot of sense if you know how to calculate it, because um, the buoyancy force is equal to the weight of the water which is displaced by the hull. And that's here visualized by the black part. Um, so let's focus. We have two things to solve: the weight of the boat and to calculate the buoyancy force. Let's start with the weight. We have to consider fixed loads. There's the hull, there's the structure, like planking, the beams, all that, even the insulation, and there's a fit out: windows, doors, parquet, kitchen, and technical installations, engines, batteries. And if you really think about it, there's quite a lot to it, and often things get overlooked. Talking about overlooked or underestimated: variable loads, passengers. Yeah, that's easy to calculate. Maybe average of 75 kilogram per person. Furniture. People underestimate how heavy furniture are. Personal belongings. There's a reason, there's a joke with sailing boats that the line where the water line is gets always moved higher every year because people just put more and more stuff on the boat. So personal belongings is as well often underestimated. Tank content. Think about 1,000 liter of fuel or water is 1 ton, has to be considered. Snow. For people who, like me, live somewhere where it can snow, it can be quite heavy load, which has to be considered. So make sure you really have a good grips on how to calculate the weight of the boat. How do you do that? So there are different ways to do it in a spreadsheet. You can do just a general top level calculation where you just list the main components of the boat and you estimate, or maybe someone who builds it for you gives you the cost, give you the weight, but this is not that accurate. So we have to work with a high contingency. For everyone who's really into buying, building, designing a houseboat, I would really go a bit more detailed calculations, where you have again on the left the groups or the components, hull, superstructure, and so on, but you really go down into the parts. And this is something I talk about in my book as well. This part list is really important because you have to know what you have to order. So I would include as well things that don't weigh that much, but just list everything you can think about. Write down the specification you need it later for ordering anyway. The quantity, unit, so how many units of each, how many pieces, square meters you have to buy, the weight of each unit, and then you can calculate the total of each component or each part. Simple calculation in Excel where the total is just the quantity times the unit weight. Very simple Excel calculation. You can as well have a mixed calculation where you have sometimes top level, sometimes drilled down, and you can as well use helpful numbers. In my book, I calculate, for instance, the weight of a typical floor, a typical wall, a typical roof with different kinds of insulations. So you can use these measures, and then you'd only have to calculate the square meter of roof or walls you have. For internal walls, you can work with linear meters. Whatever it is, don't forget your contingency, because you will surely have forgotten something, and as time goes you get more precise. Some tips from me: get other values from other projects. If you have a houseboat which kind of reassembles what you have in mind, see how much that weighs, because chances are you will end up in the same weight range. Go on your head through the construction process. Now think about, okay, I do this beam, how do I connect it? Okay, I like the beam hanger, I need the screws, okay, insulation, wait, I have to have a membrane outside. So go through it and then detail your part list that you don't forget anything. Start top level, so even if you don't know exactly how you will do, I don't know, the roof, say roof, make an estimate, and as you go you just detail the roof beams, the insulation, the roof membrane, and so on. And my tip is just include everything. Even if it does weigh that much, later when it comes to designing, ordering, you will be very appreciative that you have a complete list of all the parts of the boat. And again, don't forget the contingency. Often people think, I don't need that much contingency because they're aiming to buy a cheap hull and they know the buoyancy is limited, but chances are it will be heavier, so don't forget your contingency, and rather overestimate than underestimate. All right, so we have the weight force. Now we have to calculate the buoyancy force. But this is a bit of a tricky thing because we don't really know where the houseboat is. Is it deeper, higher? And depending how deep the boat is in the water, it as well changes the buoyancy force. So we have to know where exactly the buoyancy is equal to the weight force, and this is given at the actual draft. This is the draft where the boat will later in real life float. So how do we determine the actual draft? Let's look at this hull a bit closer. So it's just a round hull, composite, HD polyethylene, something round. So what happens if we now push this hull into the water and we observe the displacement? So it is the volume of water displaced, and the weight of the water is the displacement in kilograms. So let's do that together. Let's push it in and we record the volume of water. First it rises steep, and now as the round hull gets a bit narrow on the top, the displacement rises not so much. It's a critical range, the last few 10-15% of a round hull. So now we have a buoyancy curve, displacement curve, and if we now mark on this axis with the displacement the weight of the houseboat, go to the line of our displacement curve, then we find on draft the actual draft. easy. So the thing is just we have to create a displacement curve. There are a few ways doing it, and I will run through all of them. You can get it from the manufacturer. If you have a prefabricated or a designed hull, they will give you a curve. You can calculate from a 3D model. You can measure it if you have, for instance, an existing hull. You can calculate from fixed dimensions. You can calculate it by parametric calculations. So I will go through all of that. First, displacement curve from the manufacturer. That's the easiest way, and very often people opt for pre-manufactured hull. So you get either a curve, sometimes they're a bit color-coded to tell you the no-go zone where it's unsafe. There's kind of a yellow zone where you don't want to go in there, and you try to operate most of the time in the yellow, in the green zone, or they give you a curve. And of course, you can make the curve as well into, you can convert the table into a curve. Same, but different. So that's the curve for when you buy something from a manufacturer. 3D. Nowadays, a lot of people use CAD, computer-aided design. It requires some skill, but it's very rewarding because you see what you design, how it will look like. It gets the most accurate results. And downside is a bit, it's hard to modify your hull, yeah? Because often these complex designs to really modify not that easy. You can stretch, you can modify, but it's not that easy. But that's a bit of a downside. We need a program that can work with solids, so not just surfaces. And I often use SketchUp. It's a free program, but I can't believe it's free because it's so powerful, and it does the same thing that many expensive things do. So what I show you now is from SketchUp 2017. I think it's the last free version you can download, but all older and newer versions do the trick. So you create the hull in SketchUp. I'm not really going through how to do that. There are great tutorials online, but just imagine you have something like this. For the calculating the displacement curve, don't worry about anything inside like stringers or bulkheads, just the outer hull. You click it all and you make it a group that it can't be changed that easily. Then you go deselect the group again and you create a surface bigger than the hull, which kind of represents our water surface. And by the way, this is how a simple way doing it. Other programs have maybe easier ways to do it, but this is how it works in SketchUp. If you have some better solution, let me know, but this works for me. So you have now the hull, you have the water surface. Now you select the water surface, you know it's getting here blue, it's selected, you cut it out, and you, no, you don't cut it out, you move it to where you think, where you want to measure the displacement. Yeah? So I just here moved it up, I don't know, 70 centimeters, and now we cut it out, open the group from our hull, and we paste it inside. Then we select the whole thing. So now the group is open and we have the hull and the water surface in the same sphere. So they're all in the same area, in the same group. And now there's something very cool what SketchUp allows us to do. It allows us to intersect the water surface with the hull. So if you selected everything, the water surface and the hull, you click right mouse click and you choose intersect faces with selection. And once you move it, just have a look where the water meets the hull. At the moment there's no line, but once you click with selection, you see there is now a line. So SketchUp now created a line where the water surface meets the hull. If we now delete all the things from the water surface and from the hull around it, then we left with the volume of the hull that's under the water for this particular position of the water surface. So if we now close the group and we go onto this group and click in Windows, on the menu on the top, you go to default tray and then entity info. Once you click that and this rudimentary place shape of our hull is selected, you will see a little window popping up, and it gives you the volume, which are now highlighted in yellow. So that's the displacement. It's not displacement yet. It's the volume now in cubic meters. Assuming like 1 liter of water is about 1 kilogram, or 1 cubic meter is about 1 ton. This is now equal, this here, 26 cubic meters is the same like 26 tons. That's the displacement of this hull at this position of the water surface. So if you want to now choose more positions to calculate more positions of the water surface, you just either in the menu click undo, or in Windows you choose Ctrl Z, and you do so many Ctrl Z until you again have the surface outside the volume of the hull, that the hull is not intersected with the water surface anymore. Because when you now move the water surface to a new position, you have to intersect again. So you just go back to where you started with Ctrl Z with undo. So to create a displacement curve, you have to do this exercise at a few positions, but not at too many. So if you look at this hull, like I showed earlier, it's a bit of a more like a lot of square edges. We know that the displacement changes linear when there's no grave change in the design of the hull. So I would recommend you do measure the displacement here at the end of the keel, here where the lower bit kind of makes a kink up to the sides, and there where the straight line, the straight surface of the hull starts, and on the top. That gives you in the diagram below 1, 2, 3, 4 points, and because we know the displacement changes linearly between them, we just can connect them and we have our displacement curve. You can do that as well with round shapes. There I would space it a bit more evenly, like here again 4, 5, let's make 6 points. Here the thing will not change linearly. So when we now connect straight lines, it's not 100% accurate. When you do it in Excel with your results, you can smoothen the line out, but I now impose in the end even the straight lines are quite a good result. And for just designing and knowing where your house will float, this is more than accurate. But if you use Excel, you can also smoothen the line and you have a very accurate displacement curve. All right. Curve from incremental measurements. If you have a hull, and that's mostly important when you drive something secondhand, there's no documentation and you have no displacement curve, so how do you do it? You kind of measure every so often the width, the length of the hull. I kind of always recommend every 10 centimeters, and you measure that and put it in table. So the draft calculate from the lowest bit of the hull, and every time we measure width and length. The displacement we can now calculate by just multiplying the width time the length time the increment of what we choose to measure. And in this example, it's 10 centimeters, so it's times 0.1 meters. And then plus the displacement of the increment before. So you kind of slice the hull up You calculate for each slice the volume, and then you add up each volume with each other, and that's how you create this displacement curve. Again, this is an easy and fast way. It works for hulls that are a bit complex and like curvy hulls, or old ones where you don't have a curve. And actually the accuracy is really quite accurate. So if you put this table here now in a curve, yeah, it gives you a very nice displacement curve and really quite accurate. All right, now we get a bit more technical and a bit more interesting, because often what happens is yeah, you have shapes where you maybe don't want to go out and measure every 10 centimeters, or you don't want to build the whole module in CAD, so you can actually calculate it. Requires some mathematical skills. It's very accurate, and it's hard to use for non-standard shapes. So if you have a boxy shape, square, or like very few angles, or the round shape is perfect, it's a very nice way to use the calculation, but nothing which is too round and too crazy. So again, I come back, it's probably the one of the easy examples, the two round hulls. Let's look at that hull a bit closer and look at the kind of the variables. It's a diameter, the radius is half of the diameter, and we want to calculate the submerged area. And h is in this time the draft, it's the height of this submerged area. Displacement, easy, is the volume of the hull under the water, and is calculated by the submerged surface. A is for area, it's the surface, times the length of the hull. Okay, so far so good. Now it gets a bit more complicated, but this is the downside of the mathematical approach. If you look up in the internet how to calculate the submerged hull, you come up to an equation here. And this is how you calculate the submerged area. Now the displacement is just this submerged area, is in the square brackets, times the length of the hull. But now just one thing I want to add, n hull, n is for number, not to forget that in this for this boat we of course two hulls. So just this displacement is the volume of this round shape times the length of the hull, and then times 2, because we have two hulls. So just on a note, when you use these functions like arc, cosinus, sinus and everything, make sure that your program works in cosine. It works in radians and not degrees. You can quickly check that by you just type in your program, maybe if you use Excel, type in the sinus of 90 degrees, and if it results 1, you are in degrees, which you don't want. If the result is 0.839 and so on, you set to radiant. In my book as well, show you how you can swap from one to the other, from degrees to radians. It's not that difficult. You work with pi and all that. But for the time, I just assume that your program is in radians. When you enter the variables into this equation, you have to be careful with the units you use. So if you want to calculate the displacement tons, you have to use for all dimensions meters. So that's how this equation on the top works. So let's look into this a bit more detail, how it works practical. So we create an Excel table, and we put on the left side the draft, and then in the box on the right the variables. So it's like the kind of parameters. So in this time we have the diameter, the radius, the length of the hull, and the number of the hull. And you see as well here on the top how this equation on the top translates into an equation Excel, for instance. But you can as well use any like open source or any other spreadsheet program. So you put that in, and you can now use this table and move it down. Before I go down, I just want to tell you that please note that when you use in this equation a variable that will always stay at the same spot, you have to put a $sign before the relevant row. So you see, for instance, in the equation it's $4. So $4 is the radius of the hull, and we always want the equation to refer to the row number 4, because I now show you a trick how you can move that equation down to all the other lines, and we always want the equation to be updated with all the other variables, but not with the ones in the parameter. So you hover over this little square box on the bottom right of this green little square, which contains our equation, and your cursor, which is normally like an arrow, will change to this little black cross. And if you now hold the left mouse and you pull it down, then you copied the equation to all the different rows. So you see here that there's a bit of an error created. So there's a number error in the draft 1.1 and more. And the reason is, at the moment our parameter says the diameter of the hull is only 1 meter. So the equation doesn't work for the hull being deeper than it's actually big, like it is below the surface, already capsized. So the equation has a problem. It doesn't really matter, but if you want to change it, you can here add to the equation like an if function, which says just if the draft, it's here in this case A3, is larger than the diameter, which is F3. So if A3 is a draft and F3 is a diameter, if this is bigger, then don't put in a result. And just here it's two quote marks. That means please leave it empty, and then the spreadsheet will look like this. Everything over 1 meter will be blank. So this one you just can mark here. I made it in yellow, the if function. So you can use, for instance, Excel to translate now this table into a curve, et voila. You can make the increment smaller. I had it here like every 10 centimeters. It's more than enough to calculate the dimension. So no need to go much smaller, but it's a very nice outcome, this typical scene curve for a round hull. All right. Now let's do the same thing. Calculate something with simplifications. Because let's assume you don't have a round hull, which is not that simple. Let's assume you have something like this. Straight lines, and you want to calculate it. This has the advantage over the CAD file, that when you work with variables again, you can very simply modify the hull, because chances are that you maybe have a hull that's too small or too big, and it would be easy just to change a variable and see what you have to change to make it work. So I'll show you a bit how you can first I go, okay, the advantage for this parameter design. You can use it for hulls with straight lines, and now the calculation, you don't need the CAD program, very accurate, and it allows you to modify the hull. Okay, it does need some mathematical and geometrical skills, but I will run you through it now, step by step. I use Microsoft Excel, but as I said, other programs work as well. Simplifying. So you would go crazy if you would try to calculate all the little bits here of this propeller canal and the tapered end of the keel for the propeller shaft. So just simplify it and reduce the number of curves but try to balance the volume. And I show you now, see what happens. Now there's a yellow line, and you see the keel is, for instance, I make now a square keel, which is halfway between the tapered end of the keel, and I totally delete the propeller canal because it's really small, and I come up to this design. The simplifications are very simple. It doesn't change much with the buoyancy. Let's have a look what I would do with this bow. There's so many corners, so I take it slowly. You see, I reduce the number of kinks, make the keel boxy again, and it's the same volume. And I will later show you how accurate it still is, nevertheless, to the simplifications. Okay, we have to now chop our hull up into little pieces. Yeah, we again have a lot of dimensions, and it doesn't matter what you call them. You just have to know what is what. Make a drawing like I have here. So width overall, width of the side, width of the lower bit, width of the keel, length of the keel. Just have all the variables. And now the chopping up. Longitudinal. Whenever the form of the hull changes, we declare a new area. So 0 is the overhang of the bow, 1 is where it gets tapered, 2 is the section before the keel starts, 3 is the long section where the cross section is constant, and so on. You do the same as well across the hull. You see where it starts. C is in the middle with the keel, B is with the flat bit, A on the sides, and you do it as well from the top to the bottom. So I is the area of the keel, double I is the one, Roman second is from the little bit with a low angle on the surface, 3 is where it rises up on the side, and 4 is the one which is just straight on the top. Okay, so now I want to show you how this works with calculating the different areas and why we chopped it up in so many areas. So this here is the section C3I, because C it's in the middle, 3 it's on the bottom where in the middle where the keel is, and I that's where it's on the bottom. And if you look at it, it's just a square, and it's very easy to calculate. It's just the length of the keel times the width of the keel times the height of the keel. Done. Let's move on. Let's have a look. This is now, again, it's in the 3 section in the middle. It's still in C, but it's now in Roman 2, double I, just above. And look at it. It's really simple to calculate. The length of the keel times the width of the keel, and now the heights of the lower section. You see that on my dimensions on the right. Let's get a little bit more challenging. Now we have in the B side. So B is left and right of the keel, still in section 3 and still in Roman 2. You have no two square like little wedges, and you can actually move them over each other, and you have again a square. Volume easy to calculate, length of the keel, width of the lower bit times heights of the lower bit. Okay, this is now again a simple one. It's again in B, again in 3, but now for Roman 3, the 3 times I. And you see again, it's the length of the keel, the width of the lower section, the heights of the middle, and times 2. Again, if you really visualize it like this, yeah, it's really easy to see. I finish with, okay, 2 more. This one in the front, for instance. This is now in section 1, section C, and section Roman 3. And again, it's like a wedge shape, and you can calculate the volume by the length of the bow, the width of the keel, and the heights of the middle section, which is the height of Roman 3 divided by half, because it's a wedge. This one is a bit more complicated, but again, with all these shapes, you can as well look them up in the internet. And when you simplified your design well, you will have an easy way of calculating it. This is now here in section A, section 1, and again Roman 3. And there's the calculation how you do it. Okay, you will see when you go through it, it's not that difficult. It's a bit of time, but it's again based on the variables. So where does all this go? We create a table, and now we have to have in this table all the different chunks of the boat. Here we see 0, 1, 2, 3. These are the longitudinal sections. Now highlight in yellow is ABC, and we have ABC for each of the longitudinal sections. And then now far left, horizontal sections, these 4 sections again, we have for each of the longitudinal and each of the cross sections. That is a lot of little volumes, but if you really then think about it, there's a lot of volumes that don't exist, and that's now here blanked out because for instance 0, that's the overhang of the front. In 0 you have only something in Roman 4, only on the top bit. There's nothing below, there's nothing in Roman 1, Roman 2, Roman 3. So in the end you see you only have a handful of volumes actually you have to calculate. So we spoke about that earlier, and I just give you a few examples how I typed it in. Here, for instance, Roman 4, I just merged into one big volume, which is just the length, overall length of the hull, the overall width of the hull, and the height of the top bit, which with the vertical sides. On the draft on the left, yeah, you always start one section there with the draft where it starts, which is the end from the previous draft. So here this 0.5, this section starts now at 0.5, and it starts there where the previous section stopped. So I just copied that over. And the next one, you have to work with the variables. So this time it's again the draft from before, the left one, from, and then plus for Roman 2, the height of this section is the height of the lower bit. So just think about it, where the drafts of each slice you made for your boat, where it stops and where it starts. The displacement for each section you calculate by the previous draft. We had that earlier, so we calculate the slices of the hull, and you just always add the displacement of the slice before. So which you see here, so displacement, the sum of all sections in blue, plus the previous displacement, which I highlighted there in green. When you have your box of parameters, you often will find that some parameters double up. For instance, I have in my drawing that I want to design the length of the stern overhang, the offset where the keel starts in section 4, the overhang of the bow in the front. So in the end, the length of the keel I can calculate. So in my table I calculate that as well, and I mark this field gray to remember that I not change it. So when I later play around with my design and I change the overhang or I change the width of the hull or whatever, these equations will be, these variables will be calculated automatically. Okay, here I just type in for an example section 3C Roman 1. That was the keel bit is just vary, length of the keel, width of the keel, height of the keel. So what we calculated earlier. All right. Let's go further. We have now these displacements for the different sections, and we just take the draft on the left where it always starts and the value of the draft, and we put it into a curve. So I spoke earlier about the simplifications. So I want to show you, this is a hull which I actually built. And now with simplified calculations, we came to this curve. But because I as well did it in CAD, I can as well calculate exactly the volume. Now with all the propeller canal and all the bent steel. And if I superimpose that, now these curves match. Yeah. So you see, even with my simplifications, I created a displacement curve which is spot on. So don't stress too much simplifications, just make sure that all up the volumes are kind of stay the same. All right, so putting it all together, we calculated the displacement curve. We calculated the actual weight of the boat. With this weight, we can on the displacement curve determine the actual draft, where our boat will float. And secondary, we know then as well the actual displacement, which is the weight of the boat. When we continue the curve, the displacement curve to the fully submerged hull, we can as well see in this diagram the freeboard. So these are the basic figures of a displacement curve, how to read it, how to understand it. So my recommendations: minimum freeboard. So for protected waters, I know most of the time it's all flat and glossy, but I still nevertheless like 70 centimeters of freeboard. Just imagine there's a big barge plowing past, or maybe even a stretch of water where there are bigger waves. You don't want that water comes in. So 70 centimeter, I think, is very decent. And if you have a construction like a catamaran where you have timber on the bottom which is exposed, I would really have at least 50 centimeters. So even if there's a big wave, if it gets occasionally wet, it can dry out. But the worst thing is, like, imagine 30 centimeters. That's nothing. So if there are waves and it's constantly touching timber, it will rot, and that's not what you want for a long life expectancy. All right, buoyancy reserve. This is as well especially for round hulls. Make sure you have plenty of it. Even if you think you're in control and you know how much belongings you will have later and how many people will come, make sure you have more, because there might be a party with more boats, or there's the china you put in your kitchen is more than you think, or you put later a generator, or you put some new parquet in there. So make sure you're on the safe side. All right, so what's next? First of all, I hope you enjoyed this tutorial. Hope it was helpful. Freeboard is a very important bit. I see too many boats too close to the water. I hope it doesn't happen to you. And enjoy the scoping and design process. It's really rewarding. You create your own boat. You will love it. But spend the right time in the designing process, because that's where you make the most impact. Follow me on Facebook, Designing and Building Houseboat, if you like. Every now and then I post something, and if you have some comments, always welcome. Have a look at my book, Designing and Building Houseboats, available on Amazon and all the different shops, and it's really packed. You saw at the beginning the content. I show you how to calculate a beam, a propeller shaft, how much water, the batteries, how to calculate how much heat you lose, the weight. It's very comprehensive. If you need help, I'm really happy to consult. Just send an email to mail@designingandbuildinghouseboat.com, and we take it from there. So best of luck with your project, and all the best. This is Stefan.